Hello, in this video I am going to talk about acid-base equilibria, the topic that we started dealing with in class. Let me start by discussing how we calculate pH for a strong acid. So one of the 7 strong acids that we discussed in class is hydrochloric acid. One thing we need to remember about strong acids like hydrochloric acid is that when you dissolve them in water, they dissociate completely. So we don't have an HCl remaining behind. So the HCl becomes a hydronium ion and a chloride ion. So that's complete dissociation taking place. Now, when you to calculate the pH of a solution, what you are interested in is the concentration of the hydronium ion, or the concentration of hydrogen ion, or the proton in solution. And one thing that we need to notice is that when you dissolve hydrochloric acid, the amount of hydrochloric acid you have dissolved is the same as the resulting concentration of the hydronium ion. And the calculation of pH of a solution, you just take the negative logarithm of the concentration of hydrogen ion, or the negative logarithm of the concentration of the hydronium ion. So just take note that the hydrogen ion here and the hydronium ion are the same ion. Actually, in water, hydrogen ion is present as the hydronium ion because hydrogen ion has what we call higher charge density, as we discussed in class. So if you want to calculate the concentration of a strong acid, you just take the if you want to calculate pH from a strong acid, you just take the concentration of that strong acid. In this case, we have 1 molar HCl as our strong acid. So we just take the concentration of the strong acid and get the negative logarithm to base 10 of that concentration, and then we get our pH. So in this case, the concentration of hydrochloric acid is 1 molar. So the pH is equal to negative logarithm of 1 molar. So the logarithm of 1 molar is 0. What does it mean? It means the pH of a 1 molar hydrochloric acid is equal to 0. But now this is a strong acid. Now let's move on and see how we can work with weak acids. For a weak acid, it's a little bit different. It's a little bit more complicated than just a strong acid. We need to know that the weak acid will only slightly dissociate in water. One example of the weak acid is the acetic acid. which is shown here. The acetic acid will dissociate in water to form a hydronium ion and an ethanoate ion. So the acetic acid loses a proton to water to form this hydronium ion, and the resulting ion is the ethanoate ion. So for reactions, as you can see here, we have a double arrow. For reactions that have a double arrow, it means we can get into an equilibrium situation. So for acids, the equilibrium situation is shown by the expression below. So this expression shows the equilibrium situation of a weak acid, Ka. The Ka is known as ionization constant. It is the equilibrium constant for an acid equilibrium. And as we know, equilibrium is given by the products to the power of their coefficients. They are the numerator over the reactants to the power of their coefficient. And in the end, you need to have an equilibrium constant as a value. This equilibrium constant is very important because it will tell us the extent to which the dissociation has happened. So if you have a larger Ka or a large Ka, you know that there is a lot of dissociation that has happened. If you have therefore in that case we have for a larger Ka more dissociation. Here I put less, but it should read more. This one should read more. So we have more of hydronium ion in solution and the ethanoate present in solution because the Ka is large. Or we have more of the products for a larger Ka. For a smaller Ka, it means the extent of dissolution of dissociation is very, very small. So it's only a very minimal amount of the reactants that have turned into product. It's a very minimal amount of acid that has dissociated into the ethanoate ion. So just repeating what we had, Ka is the ionization constant. The value of Ka determines the extent of dissociation. The larger the Ka, the more dissociation, and the more H and CH3 present in solution. And here we know there will be less of CH3COOH present. For a smaller Ka, the opposite will happen. So for smaller Ka, we will have more less dissociation, so we'll have less of H and CH3COO, while here we'll have more of H and CH3COO present in solution. So what we have here is the opposite: a larger Ka, more H and more CH3.